Okay. Oh. Let's start the lecture. Last time we introduced how to solve non-homogeneous problem, including non-homogeneous PDE and non-homogeneous boundary condition. Actually, for non-homogeneous boundary condition can be transformed into a homogeneous boundary problem. Okay, by a transform of the unknown function. So, but the equation, even if the original equation is homogeneous, the new equation might be inhomogeneous or non-homogeneous. Therefore, anyway, we need to solve non-homogeneous problem. But to solve non-homogeneous problem with homogeneous boundary condition, you simply write down your corresponding eigenvalue problem, solve the eigenvalue problem, then you obtain the sequence of eigenfunction. Then you expand everything, the unknown function, the non-homogeneous part ftx, and also the initial condition, okay, into the expand them in terms of the series of the eigenvalue function. Okay, then you determine the coefficient for the expansion of the unknown function u, that is t and t. The t and t will satisfy how to say ODE. You satisfy an ODE. Okay, the ODE can be solved. Solving the ODE, you obtain your Tn, therefore you obtain your solution. Okay. Now today we will study a new chapter, chapter 6, about integral transform. This is also a very useful method for solving ODE or PDE. We mainly study Laplace transform and the Fourier transform. Okay, the transform method and our previous method. Our previous method is separation of variable and then expansion. We talked about last time on Thursday. Okay, these two methods essentially the same. But they're only suitable for bounded domain problem. The problem is bounded interval, 0 pi, 0 L. But if your problem is sitting on an unbounded domain, say the positive axis, the whole positive axis, the interval is the length of the interval is infinite. So you could not use the separation of variable. Then, but our Laplace transform and the Fourier transform will be quite suitable for those problems. Now, I think you should have studied ODE, ordinary differential equation, and then it should contain the Laplace transform. I don't know what you learned in ODE, but I will have some review. But of course, we do not have time to go into detail. We simply explain the concept and present the result. We will not prove most of the result here. So transform is a transformation. Inputting a material, you have your product. Okay, our material is a given function. For Laplace transform, the function is defined on the positive axis, 0 infinity, the interval. Okay, then we will obtain a new function. The new function denoted by f tilde or denoted by LF. This new function, the variable of f is t, but the resulting function f tilde called the Laplace transform of f, the variable is denoted by s. So f tilde, the value of f tilde s, that is LF s, is this integral. This integral is an integral on t. So e minus st ft dt. Okay, so because you know s is also positive, or s is also non-negative. So since the expression decayed very quickly, from this definition you will see that for many f, this integral is converged. Of course, the value of this integral depends on the parameter s. Therefore, the value of the integral is a function of s. So the function will be denoted by f tilde. That is our Laplace transform. So for the Laplace transform, sometimes we also denote by capital F. The notation f tilde is invented by myself. because for Fourier transform we use f hat, and the inverse of Fourier transform we use f dumb hat. Okay, so but for Laplace transform, maybe we should also have some similar notation. This will be convenient. But in most literature, we use LF or capital F. So small f is the original function. Capital F is transformation, the Laplace transform. Anyway, this is just a notation issue, not essential. Now let's state the property of the Laplace transform. So for most of the function f, its Laplace transform exists. F is good enough, then the Laplace transform exists. For example, f is piecewise continuous and grows not faster than exponential growth, then the Laplace transform will exist. Okay, and it has the following property. The first is that the Laplace transform of the sum of two functions equals the sum of their transform. Okay, and also a multiple of f, the Laplace transform of a multiple of f equals lambda times the Laplace transform of f. So these two property means that the Laplace transform given me a function, I produce a new function. This is a transformation. This is linear. Okay, linear property. Like our linear partial differential operator. Okay, when we introduce linear PDE. Now, this is a state. The property is stated using my notation f tilde. But if you like, you can also state the same property in terms of capital L. Okay. So this is equivalent. These two representation is equivalent. Then the next property is crucial for our purpose. The Laplace transform of f prime. F prime is the derivative of f. Okay, f is a differentiable function. Its derivative is a new function. So the Laplace transform of this new function equals to what? Equals to s times the Laplace transform of f itself, subtract the value of f at 0. Okay, so this is crucial for us. Why? Because after making a Laplace transform, the differentiation becomes multiplication. Okay, there is no prime on the right hand side anymore. Okay, so this is again in my notation. But if you like, you use the capital L notation. L f prime s, that is the Laplace transform of f prime equals s times the Laplace transform of f, subtract f0. The same as what I said before. Now, from this property, it is we can understand why sometimes we don't want to use the capital F notation. Because for your f, you use capital F to denote its Laplace transform. But if you using this pattern in this style, what should you use to denote the Laplace transform of f prime? Okay, that is we could not do this. But if you use our f tilde notation, you see, f prime tilde is the Laplace transform of f prime. So this justifies my introduction of this f tilde notation. Okay, but this is only legal in our classroom, even not for our test. Maybe the GSA grading your test do not know my image of this notation. Anyway, now the third property is that double prime, second order derivative, because most of the PDE will encounter is second order. Therefore, we also need here is first order, this is second order. Of course, for Laplace transform, even for nth order the derivative will have a more complicated property, equality, but we don't present it here. Okay, so for second order derivative, the Laplace transform of the second order derivative equals s squared times the Laplace transform of f, subtract the value of f and its prime, its derivative only at 0. Okay, anyway, we have this equality. Again, this can be expressed in terms of the capital L notation. then it looks like this. Okay, so these are some properties of Laplace transform, simple property. We don't have time to prove it here. Now, the next property is about convolution. Convolution. F star G star is convolution. I will explain what is star. The convolution, I missed something. The Laplace transform of the convolution of F equals the multiple of the Laplace transform. Okay, I have misplaced that. I'm missing the tilde for the convolution. Here, the convolution given two functions f and g defined on the positive axis. The convolution of this function is a new function denoted by f star g. The value of this function at t is this integral. The integral which is respect to tilde to top. Okay, that is the definition of a convolution. Now, apply Laplace transform to the convolution, you will obtain the multiple of the Laplace transform of f and g. So Laplace transform convert convolution into multiplication. It converts derivation which into multiplication. Okay, and for this reason, the inverse Laplace transform. Laplace transform, you can consider is inverse. Laplace transform is one direction, inverse is the reverse direction. Given capital F, find the small f, so that applying Laplace transform to the small f, you obtain the capital F. The small f is called the inverse of capital F and the Laplace transform. Okay, so this property is also useful. In one of our example, we will need this property. Okay, now there is still another important property I will introduce to you. Now, suppose f is a function defined on the positive half axis, and a is a positive number. Then we define a new function fa. Fa is what? Fa equals to the value of fa at t. The fa is also defined on 0, infinity, this interval, and the value of fa at t related to f, but depend on the t and a. If t is not less than a, then the value of this new function at t equals the value of f at t minus a. Because t is not less than a, therefore t minus a is also always non-negative. So this f, the value of f at t minus a makes sense. Okay, that is the value of fa at t. But because our fa is supposed to define on the non-negative for non-negative number. Then if t is greater than 0 but less than a, what happens? Simply 0. Okay, this is the definition of our this fa. Maybe you can draw a picture for this function. So suppose this this red one is the graph of f. Then maybe a is here. Maybe I should not use red. Maybe I use blue. This blue curve is the graph of f, and a is here. Then what's the graph of fa? Fa is shift f to a. No. Then 0 here. Between 0 and a, it is 0. Then after that, the graph of fa is simply translate the graph of f to a. Geometrically, the fa is such a function. Okay. Then using this fa, we have this very useful property. The new function, the Laplace transform of this new function equals this exponential times the Laplace transform of f. Okay, maybe I will prove this property here. From this property, applying the inverse Laplace transform, to both sides of this equality, we see that the Laplace inverse transform of the right-hand side equals the Laplace inverse Laplace transform of the left-hand side. But since the left-hand side is the Laplace transform of FA, okay, applying the inverse transform, the left-hand side become FA. So we have this inequality. Okay, these two are equivalent in some sense. So we only need to prove the first one. The proof is easy. We will not present difficult proof in this course. Well, we want to prove this equality. We just write down the left-hand side by the definition of Laplace transform. The left-hand side equals this integral. But you see, FA is 0. FA is 0 when t between 0 and a. Therefore, this integral can be written as, instead of 0 to infinity, a to infinity. Okay? Now we change the variables. T minus a, we call it tau. Therefore, this becomes f tau. Making the change of variable here. Okay? Changing variable, the last integral becomes f t minus a become f tau. Sorry, this is tau, not t. Misplayed. Okay, f tau, and t is tau plus a. Then when t equal to 0, tau is when t equal to a, tau is 0. Therefore, the limits of the integration is 0 to infinity. But e to the this part is e to the minus sa, e to the s tau. The e to the s tau part oh no, wrong. The e to the minus s tau part and f tau precisely the Laplace transform of f. But this e to the minus sa has nothing to do with the integrating variable. It can move out of the integration. So we get e to the minus sa, then remaining e to the minus s tau, f tau d tau. But this is just the Laplace transform of f at s. So this proved our first equality. Very easy, just a simple changing variable. Okay, so that is the property of Laplace transform we need. So we know its definition. We have this crucial property we will apply. And also we know that we have an inverse Laplace transform. So the idea to apply the Laplace transform to solving differential equations is that because Laplace transform turns the derivative into multiplication, So an ODE, after applying Laplace transform, it becomes algebraic equation. There is no derivative anymore. Therefore, it is an algebraic equation. So it is much simpler to solve than differential equation. And a PDE involving several variables. You apply Laplace transform to one of the variables. That variables disappear. Then you have if you have two variables, killing one variables by Laplace transform, because of that derivative which with respect to that variable become multiplication. Okay, so after taking Laplace transform, the variable disappear. You only have a derivative of the remaining variables. Then this is an ODE. You know how to solve ODE. Okay, so we can say that all the methods for solving PDE almost reduce the variables, convert the problem into solving ODE. Maybe not a single ODE, maybe a families of ODE. All our methods previously we encountered the separation of variable and our expansion method we talked about on Thursday can be considered as solving families of ODE. You know the TNT. We have a n1, 2, 3, and so on. We have infinitely many ODE to solve. Okay. Now let's consider example. First, warm up example, ODE problem. So this is a second order linear constant coefficient, no homogeneous ODE. Okay. So we have an initial condition. X0 is 0, x prime 0 is 1. We want to solve this problem by Laplace transform. How to do this? We apply the Laplace transform to both sides of the equation. Since we only has one variable t, of course the Laplace transform is taking respect to t. So the left hand side is what? The Laplace transform of x double prime. We know that Laplace transform convert derivation into multiplication. So in one of our property, in one of our previous property of Laplace transform, I use capital X to denote the Laplace transform of the small x. Of course, you can also use my notation s square x theta s minus s x0 minus x prime 0. No, this is not misprint. This is the original function. The value of the original function is derivative at 0. Okay, this is not a misprint. We only have the first term, capital F, capital X. That is the Laplace transform of our function, small x. So this is the Laplace transform of the left-hand side of the equation. So from this, we see we can observe the advantage of the method of Laplace transform in solving ODE. So in general, we solve ODE, the traditional method is to find the general solution containing two, because this is a second order ODE, the general solution contains two arbitrary constants. Then you use the initial condition to determine the constant C1 and C2 and obtain the precise solution of this initial value problem. Okay, but using the method of Laplace transform, the initial condition has already been encoded in your computation. Okay, that is the advantage. Now, this is the Laplace transform of the left-hand side. Now, the right-hand side, this is just the x double prime. We still have an x, that is capital X. Then this equals the Laplace transform of the right-hand side. Now, for the functions we encountered from time to time, there are some table of Laplace transform. You can check the Laplace transform of this function. Then you see that the Laplace transform of this function is s divided by s squared plus 4. Okay. Of course, you can compute this by definition. By the definition of Laplace transform, but that takes some time, maybe 20 minutes to do the computation. But you can check the table of Laplace transform to get the result. Okay. So now we're using the initial condition. Using the initial condition, we see that x0 is 0, therefore this term disappears. X prime 0 is 1. So the left-hand side becomes s squared capital X plus capital X, then minus 1. X prime 0 is 1. Minus 1, I move to the right-hand side because x1 plus this fraction. Okay? Then I simplified this. We obtain this. Then we can solve for capital X. Consider this as a function, as an equation of capital X. Then this is an algebraic equation. There is no derivative involved. So this is an algebraic equation. We solve this algebraic equation for capital X. We see the X is this fraction. Now, the inverse Laplace transform of this function, capital X, this capital X is a function of S. After you take the inverse Laplace transform, you get the original function, small x, which is the solution of our problem. So to compute the inverse Laplace transform of this function, we decompose this function into some simpler, into the sum of some simpler function. And each of that simpler function, we know it's Laplace inverse transform. So this can be decomposed into the sum of these three functions. Okay, this is very like similar to when we take the indefinite integral for some function, fractional function. In calculus 1, we know how to do this. So decompose into these three functions. Then each of these functions, we know is Laplace inverse transform. Then we apply the inverse transform. The left-hand side, capital X becomes small x. And then this term, a third, is a coefficient. Because Laplace transform is linear, therefore you can move this a third out of the, how to say, maybe no. Yeah. Your Laplace inverse transform equals a third. This, okay? This coefficient can move out of the application of inverse transform because L itself is linear. So the inverse transform is also linear. Therefore, you can move this outside. Then just taking Laplace inverse transform to this function. Then checking the table, you know that it is cosine t. Similarly, for the other two terms, the second term is a third of cosine 2t. Okay, and the third term is sine t. So this is the solution of our ODE problem, initial value problem, second order. Okay, that is how Laplace transform work for ODE. Now we study this PDE problem. So this is a first order linear PDE, homogeneous. Okay. Now, as we know, the PDE alone could not say anything. You need to impose some side conditions. Maybe initial condition, maybe boundary condition, okay? But our PDE lies on this domain, x positive, y positive. So this domain is what for our PDE. We need the domain to study your PDE. This is our domain, okay? Now we have these two conditions. U0 t equals sine t. So U0 t means that when x equal to 0, when x equal to 0, at this part, t is here, then u is sine t at this point. At every point on the vertical line, positive vertical line, t, then the value of u at this point is sine t. That is the first condition. The second condition, ux0 is 0. Ux0, that is t is 0. T is 0 means that you are talking about the x-axis. So u is 0 here. Okay, that is the side condition for our problem. So of course you can consider this as a boundary condition. If you imagine this PDE comes from some phenomena on a half line, okay, the positive x-axis at the initial moment, that is t equal to 0. The quantity the physical quantity is 0. Then at the boundary point, at the end point, we have only one end point, that is the origin. Okay, the quantity varies in time. Obey the law sine t. Okay, you can consider this as this problem, this colliding some physical problem anyway. But we don't care about that. We just want to find its solution. How to do this? Okay, we apply the Laplace transform to both sides of the PDE. Then the first term, which we have two variables. Both variables values in half real line. So it makes sense to take Laplace transform with respect to t and with respect to x. but we do that for t because ux 0 is 0. So when t equal to 0, it is 0. Remember our L f prime s equals sf theta s maybe minus of f0. Okay, so the value of the original function, at 0 appears here. So if you taking Laplace transform with respect to t, then when t equal to 0, this is 0. Therefore, we do not have this term. The problem will be simpler. If you do that for x, then when x equal to 0, the function is not 0. Then you have this term. This term could not be removed. So the resulting problem will be more difficult to solve. So this is why we choose to take Laplace transform which is respect to t. Then taking Laplace transform which is respect to t, the first term ut is what? Ut my handwriting is really awkward. Let's write LUT equals SLU minus U0 t equal to 0. Of course, t is a function of x. You can consider this x as a parameter, ux0. But ux0 is 0. So you only have SLU. But we denote the Laplace transform by capital U. Of course, the capital U also depends on x because your small u depend on x and t. Taking Laplace transform with respect to t, you only q u, but the variable x remains. Okay, but if you introduce a new variable s, simply you can regard this as replacing the variable t by variable s. Okay, so the Laplace transform, maybe I should Laplace transform of ut xt equals s Laplace transform of uxt. That is s uxs. Because the u0 is 0. We already applied it. So anyway, S capital U is the Laplace transform of ut, and the Laplace transform of ux is uxxs. I will explain this later. This is also crucial. Then the Laplace transform of u is our capital U here. Then the right hand side is 0. Okay. So I will explain why the Laplace transform of ux with respect to t is the partial derivative of the Laplace transform of u which is with respect to x. I will explain this here. Okay. So L ux as a function of x t is what? By definition, is exponential of st ux xt dt, right? We are doing everything with respect to t. Therefore, x you can consider it as a constant or parameter. Okay. Now, taking derivative can move out of the integration. If u is good enough, taking derivative under the integration can be switched. You can here is taking derivative with respect to x, then taking integral. But I taking integral first and then taking derivative. These two can be switched provided u is good enough. Okay, u is smooth enough and decay to 0 fast enough. Then this is true. Okay, but what's this? This is precisely capital U. So we prove that the Laplace transform for ux is the partial derivative of capital U, which is respect to x. Okay. I emphasize. Our previously, the Laplace transform of a single variable function is a new single variable function. But now we are dealing with a function with two variables. We take the Laplace transform which is one of the variable. Then the resulting function is also two variables. One of the variables is the original one, x. The other, s, replacing the original t. Okay. Well, this is the new equation we obtained. This can be considered as an ODE. Now, since we have a derivative with respect to x, so we consider this as a ODE for which variable x, and this s considered as a parameter. So this can be said written as u prime. Prime means the derivative with respect to x plus 1 plus su equal to 0. Simply this. Okay? You consider the u as a function of x. And the s, of course, u also depend on s, but you consider that s as a parameter. So this equation is simply u prime plus 1 plus su equal to 0. So this is an ODE. Also, this ODE has initial condition. When t equal to 0, when x equal to 0, when x equal to 0, u0t is sine t. Therefore, taking Laplace transform with this condition, okay, the left hand side is capital U0s. The right hand side is Laplace transform of sine t. But the Laplace, checking the table, you see that Laplace transform of sine t is 1 over s plus square plus 1. So this is an ODE problem for the transformed function capital U. Of course, we can solve this problem. This problem, we can solve the problem. This is the first order homogeneous linear PDE. Even constant coefficients. The coefficients 1 plus s is not variable. It is a parameter because our variable in this ODE is x. So this is a constant variables. Okay, of course you know how to solve it. The solution is this. Then we need to take inverse. We rewrite this capital U, the solution capital U in terms of expression of minus x, multiplying what? Multiplying this function. Okay, why we do this? Because Laplace transform and its inverse only related to the variables t and the s. Therefore, when you're doing Laplace transform, the x and its inverse transform, the x is constant. So we separated this. So we only need to work with this. This is a constant, can move out of the transformation. Okay. Anyway, this is our u xs equal exponential of minus x e minus xs 1 plus s squared. Then our u is the inverse transform of this capital U. As I said before, the exponential of minus x is a constant because we are working with s and t, not x. So x can be considered as a constant. But the inverse transform is linear, so it can be moved out of the transform. Okay, so you simply try to find the Laplace inverse transform of this function. Of course, this is not easy. But by our previous proposition, L inverse e minus xs s squared plus 1. This proposition, from this proposition, we know that L inverse exponential of as capital Fs equals the inverse transform of capital F, that is small f, A, the corresponding Fa. Using this property, because the inverse transform of 1 over s squared plus 1 is sine t. The f is sine t, the small f is sine t, the a is x. The A here is our X. The A comparing the A here is our X. So we have the X here. Okay. The capital F is what? Maybe I need to explain this. In this case, capital F S is 1 over 1 plus S squared. So the small f is sine t. Small ft is sine t. So applying this property, this function is exponential of minus as. A is x. So minus as capital F. So applying the Laplace inverse transform, it will be small f a t. Small f is sine t, therefore sine xt. Okay, in our notation, sine xt. Sine xt is what? Sine xt is sine t minus x by the definition of our fa. When t greater than x, it is sine t minus x. When t is smaller than x, it is 0. Okay, so the sine xt we already done here. Up to here we already find the solution. But more this solution, because it involves the fa or sine x, this kind of notation not commonly known, so we can express in terms of using the Heaven-set function. That is when maybe sine xt. By our definition, it would be sine t minus x if t not less than x. It is 0 if 0 less than t less than x. Okay, that is the definition of our sine xt, our fa. Applying our definition of fa to this. Okay, but the htx is what? Ht minus x is 1 if t greater than x, 0 if t less than x. Okay, that is capital H. This is the characteristic function of the interval 0 infinity. So that means when t greater or equal to 0, then it is 1. When t less than t is negative, then it is 0. So correspondingly, ht minus x is given here. So you see that sine t minus x times this h is precisely our sine xt. So this is why Heaven-set function is very useful. We can use Heaven-set function to express such kind of functions. Okay. Anyway, this is the solution. This solution means that our domain is this x, y. Then we have sorry, no y. T. We have the line t equal to x. Then u is 0 below the line. Because when t is not greater than 0, then h is 0. So this solution means that t is 0 below this line, including the x-axis. This coincides with our condition for t equal to 0. Okay, but u is given here on the upper. When t greater than x, our u is e to the minus x sine t minus x. So the line t equal to x cut the domain into two parts. On the bottom part, u is identically 0. On the upper part, u is given by expression of minus x times sine t minus x. There's no h anymore because at this part h is 1. In this part h is 1. Okay, so this is our first application to PDE. This is a first order PDE. Now we consider the second order PDE. This is a heat equation. The heat equation, initial condition is 0. Ux 0 is 0, right? But for the boundary condition, what we have, our x is not restricted to an interval. X is positive, of course, also containing 0. X is non-negative. So this you can imagine a rod infinitely many long, but it has an endpoint at one side. Have a left endpoint is x equal to 0, but there is no right endpoint. It extends to infinity in one direction, such a rod. Okay, then u0 t equal to 1 means that at the left endpoint, your temperature always 1. And the solution, the temperature at infinity is 0 because this limit is 0 at infinity. Okay, so initially, but the condition is not the boundary condition and the initial condition is not compatible in this example. This is also taken from our textbook because when x is 0 and t is 0, 0 equal to 1, this is not true. So maybe the initial condition should not be 1. Anyway, you have the initial condition, but initially the load, the temperature of the load is 0, but at the left endpoint, the temperature will change each time, replacing this 1 by a function of t. Okay, then we ask what happened at every moment, every point on the load of the temperature. Okay, so you need to solve this problem. So this is, since the load is infinitely many long, you could not use our previous method, separation or expansion, to solve it. But we can apply the Laplace transform. Again, to apply the Laplace transform, we encounter a choice. What variables we take? We need to do that for t, because when t equal to 0, u is 0. So you do the Laplace transform which is with respect to t, you simplify your computation, right? So apply Laplace transform with respect to t. I just tell you that L ux equals du dx, where capital U is the Laplace transform of small u. I just explain this property. First order derivative, which is respect to the other variable, right? But now we encounter second order variables. As a second order derivative, the principle is the same. By definition, the Laplace transform of this is this integral, which is respect to t. Then the derivative, which is respect to x, can take out of the integration to get the second order derivative, which is respect to x for this integral. But this integral is precisely capital U, precisely the Laplace transform of small u, which is respect to t. Then it is a function of xs. Then this is the second order derivative, which is respect to x. Okay, so remind this. I copy this here. L uxx equal. Okay, then we apply the Laplace transform to our equation is ut equal uxx. What we have. Apply Laplace transform. The Laplace transform of uxx is capital Uxx. Then uxx to utt. Therefore, the Laplace transform is equal Laplace transform of ut. But the Laplace transform for ut is s capital U subtract s times the maybe there's no s here. I guess this s is a misplaced. Okay, ux0, but the ux0 is 0, so we only have su. So this can be considered as an ODE for capital U, as a function of of x. So the left hand side is u double prime equals su and no prime. Okay, this is the ODE that the Laplace transform of our solution satisfied. Also, so you can find the general solution. Okay, because s is positive, the general solution you can consider this as minus is equals 0. Right? So the general solution of this equation, remember the variable is x. The s here is coefficient or parameter. So the characteristic look as positive and negative square root of S. So the corresponding solution is exponential of x times square root of S and the minus. And we have two arbitrary constant C1, C2. Of course, C1, C2 depend on S. Because our variable is X. S is a parameter. You are solving a family of ODE. Okay, but those ODE, for different ODE, the variables are the constant are different depending on your S. Okay, so this is the general solution. But remember our solution, the temperature at infinity tends to 0. Using this property, we see that our capital U, by definition is the integral of this small u times the exponential. This function, when x goes to infinity, this goes to what? Intuitively, because this goes to 0. That is our requirement for the solution, right? So this goes to 0. Capital U should go to 0 when x goes to infinity. This one is a result from our requirement for the solution. Okay, this is the explanation why. Using this, we see that C1 has to be 0. Because if C1 is not 0, when x goes to positive infinity, this exponential will go to positive infinity. This solution will be unbounded, could not convert to 0. This force C1 to be 0. This force C1 to be 0. So C1 is 0. So our solution using the other, that is the boundary condition at the left endpoint x equal to 0. Our C2S is what? When x equal to 0, this C1 is vanished, disappear. We only have C2. C2S is just the U0S. Okay, by the expression for U, remember C1 is 0. You see that C2S is precisely capital U0S. But the capital U0S is the Laplace transform of the boundary function at the left endpoint x equal to 0. Then this is what? This is what? Our boundary condition at the left endpoint is U when x equal to 0. Small u is 1. So small u is 1. You need to take the Laplace transform of the constant function 1. Checking the table, you see that the Laplace transform is 1 over s. Laplace transform of for the constant function 1 is 1 over s. Okay. So we already know C2. Therefore, our capital U is now exponential of minus here. C2s is 1 over s. Therefore, this gives us capital U. We know C1 is 0. We also know what C2 is. So our U, we can write down the U. So our solution, small u, is the inverse, applying the inverse transform to this capital U. Okay. So this capital U, you can check the table. In your textbook, you have the table. You can check the table. The Laplace inverse transform for this function is this function. This is some arrow, complement arrow function, which this variable. This variable, okay. I will show you what this function is, okay, in the next page. But this equals to what? This equal to 2 over square root of pi times this integral from this to infinity. Okay. This is by the definition of this function, and this equality is by checking the table of Laplace transform. Using the table, you can compute Laplace transform or inverse Laplace transform for suitable given functions. Okay. Now I will explain to you this so-called arrows function in the next page. So ERFC. Okay. Here we have 4 letters ERFC. First, ERFC is 1 minus ERF. C is complement. That is their sum is 1. Okay, the complement of L is the complement of the L. Their sum is 1. But what is ERF? ERF is this integral. Given y, you can compute this integral. The value dependent on y. So this is a function of y denoted by ERF. We call it the L function. Okay, and our using the definition of ERF and this integral you can you should have been computed this integral when you study calculus 3, multivariable calculus. You should know this integral. Okay, so using this tool, you will see that our ERF set is precisely the integral I wrote before. Okay, this is not important, but you should know simply computation. Now let's go to the next example. Our previous example, this problem is the same as the previous one. The previous one, the small f is constant function 1. But now we consider that it is a function ft. That is the temperature at the left end point of the rod of the half infinite rod is varies in time obeying the law ft. Okay. So as before, we apply the Laplace transform with respect to t. Because why? Because the initial condition when small t, when t equals 0, the small u is 0. So because of this reason, we should take the Laplace transform with respect to t. Then denoting the Laplace transform by capital U, we have everything is the same as before, as the previous example. This example and the previous one only different at this point. Only when this u0t equals ft. The previous example, this is 1. So up to we apply this condition in our previous computation, everything are identical. So everything is identical. Therefore, our u is given by this. Okay. Applying the Laplace transform to the equation, we have an ODE, and we can write the general solution of the ODE. That's easy. Okay. And we also know that because small u goes to infinity, goes to 0, therefore C1 has to be 0. Okay, C1 has to be 0. Therefore, this is C2. This equals C2. Okay, so we need to determine the C2. C2 is what? Now we apply the boundary condition. X equals 0. Let x equals 0 in this equality. We see that. We see what? We see C2s is capital U 0s. Let the small x to be 0. Therefore, this is 1. The right hand side is C2. The left hand side is capital U 0s. Okay. But the capital 0s is what? Capital 0s is Laplace transform of the small u when x equals 0. But when x equals 0, the small u is ft. Therefore, that is Laplace transform of the small f. The small f. We denote it by capital F. So C2s is capital Fs. Okay. Therefore, our capital U equals capital Fs times this exponential function. Now, we should apply the inverse Laplace transform. The next step is to compute. Next step, we should compute the inverse Laplace transform of Fs e to the. This will be our small uxt. Okay, we should compute the inverse Laplace transform of this because this is our capital U. But before doing this, we will use this result. How to say? Yes, we need to compute the inverse transform of this. Actually, this is precisely the solution of our previous example. This is the solution of our previous example. So we know what this is. This is this integral in the answer of the result, the solution of the previous example. Why we need this? Because we want to compute the Laplace inverse transform of this capital F. But this capital F we can rewrite in this way. how to say, the inverse transform of a multiple equals the convolution of their multiple. We have this property. So because this is the multiple of two functions, then taking inverse transform by our property, this equals the convolution of their inverse. So the convolution of capital F is a small f. The convolution of this, I copy here, I wrote here. Okay? But how to compute the inverse of this function? We have this equality. Why? L of V equals E minus X square root of S over S. V is the inverse of this. Therefore, L of V equals this. Okay? Difficult or confused. You see, this is our V. V is the Laplace inverse transform of this. Okay, fraction. Therefore, applying L to both sides, the left-hand side is L V. The right-hand side, L and L minus cancel. Therefore, you only have this. So, but what we want to compute is this. We want to compute this. This is what? This is S L V. Because L V is this. This is L V. Right? This is L V. So this is L V. S L V is this. So everything unchanged, but I write this by S L V. So L inverse S L V is what? We know that L. We know that L of F prime equal S L of F minus F0. Okay. So apply, but F0 is 0. So we do not have that. If F0 is 0, we have this equality. Then we apply the inverse L inverse S L of F equals F prime. Right? L of F prime equal S L of F subtract F0. When F0 is 0, you have L of F prime equals S L of F. So applying the inverse Laplace transform, you see that the inverse transform of the right-hand side, that is L inverse S L F, equals the inverse transform of the left-hand side. But the left-hand side is the Laplace transform of F prime. Applying the inverse transform, you return to your F prime. Okay? So we have this property. But this is true only if F0 is 0. For our V here, when t equal to 0, this is 0. When t equal to 0, the lower limit of the integral is also infinity. Okay, so you're integrating from infinity to infinity. The result is 0. So our V satisfies V0 is 0. So applying this rule to V, so L V prime equals S L V, or L inverse S L V equal V prime. This is what I want to say. L inverse S L V equal V prime, provided V0 is 0. But our V satisfies our requirement. V0 is 0. So this everything here reduced to V prime. V prime is derivative which is with respect to t. So that is Vt x t. Okay? This is what I want to say. Vt x t. So this is the convolution. So our solution U is the convolution of our f and Vt. Here v is the function defined here, given here. Okay, so by the definition of a convolution, the convolution of f and vt, yes, this is what I said. The result is the convolution of f and the partial derivative of v with respect to t. By the definition of a convolution, that is this integral. But here the vt, what is the v? The v is given here. Okay, that is the solution. Of course, this looks a little complicated, but anyway, we can write down the solution. Okay, so this example a little complicated, but this is also the example from the textbook. Maybe the presentation is a little different, but essentially the same. Okay, now we consider another example. This example, the next example, comparing with the next example, almost the same, except in this example we just talk about. Here is u. On the left end point of the road, we are prescribed the temperature u. U0 t equal ft. The temperature varies in time t, depending on t. Okay, this is the prescribed temperature at the left end point of the road. But in the next example, instead of u here, we are imposing ut or ux Newman condition, Newman type of boundary condition. Okay, that is our next example. Here, this is only different from our previous example. Of course, then the idea is the same. First, we applied the Laplace transform with respect to t. The reason is that when t equal to 0, u is 0. So we need to take a Laplace transform with respect to t. Then also, of course, we also know that uxx is as no. The equation becomes uxx equal su, because since u0 is 0, when t equal to 0, u is 0, the Laplace transform of ut is su. And as we have already explained, the Laplace transform of uxx is capital Uxx. So we append this equation. This equation is an ODE for capital U, which variable s. Of course, the capital U also depends. I know. This is an ODE for the capital U, which variable x. Okay, but the capital U also depend on s. That s is a parameter. Okay, so this is an ODE for capital U. Variable is s. So this is a second order ODE. You can write u double prime minus su equals 0. Okay. Then the general solution as before is given by linear combination of exponential. Of course, the exponential and the constant also depend on s. And then again, say y is 0 because of this condition. Because this condition, small u goes to 0, therefore capital U also goes to 0, as I explained previously. So the C1 has to be 0. Okay? C1 is 0. But C2, this is, up to now is identical with the previous example. But now it's different. In our previous example, to get C2, we use the boundary condition. Now our boundary condition is different. So our boundary condition related to this example, our boundary condition is related to the derivative. So your boundary condition is your Laplace transform of your boundary function, small f is capital F. That is the Laplace transform of the ux, where x equals 0. Okay? But this is what? So you need a ux. LUX is what? LUX is the partial derivative of u with respect to x. Then x equal to 0. Because here your x is 0. Here your x is 0. So you need to compute the partial derivative of u with respect to x. So you need to compute this, you need to take derivative of this u with respect to x. You see that ux equals C2s minus x, then exponential. Right? Then evaluating at, oh, sorry, I am wrong. Sorry, this is not true. Our derivative is s, therefore this should be minus square root of s C2s e to the minus x square root of s. You are taking derivative which is respect to x, not s. Taking derivative which is respect to x, C2s constant. This is exponential copy, but the argument of the exponential should be taking derivative which is respect to x. This gives you minus square root of s. Then you evaluating at x equal to 0. So this is minus square root of s C2s. Okay, this is the result. So C2s satisfies this equation. Then you can get C2s is divided on square root of s to the left hand side. Okay, you get your C2s. Having your C2s, you have your capital U. Replacing this C2s by this expression, you get your capital U. Now you should take the inverse transform. Taking the Laplace inverse transform, we need this result. This result maybe not in our table, but in a larger table you have this result. Okay, so I will copy this here, minus e minus x square root of s square root of s equals pi t e to the x square over 4t. Okay, I will use this. Then and also our capital U is minus s e s. Okay, now let's go to the next page. So our U, our small u is the Laplace inverse transform of our capital U here. How to compute this? The capital U. The capital U here is the multiple of this function under your f. So we apply the property again. The Laplace inverse transform of the multiple equals the convolution of their Laplace transform, of their Laplace inverse transform. You inverse this, you get function of t. Then taking their convolution, that is the inverse of their multiple. Okay? L changing the color. L inverse fg equal L inverse f convolution which L inverse g. So using this property, so this will equal the inverse of this convolution which is the inverse of this. The inverse of capital F is small f. So that is. Now the first term we apply this result from the bigger table. From the bigger table, we have this result. Then, by the definition of convolution, replacing the t by t minus tau, then taking integral from 0 to t, and then don't forget the minus sign here. So this is the result of our problem. I still have one more example, but we do not have time. This example is about previously we solved heat equation up to now. Okay, but we can still apply the Laplace transform to solve this wave equation. We still have 1 minute. I explain the physical meaning of this wave equation. This is x is what? X positive. I don't think x is positive. Maybe this is a misprint. I will check. This should be x t positive. X is the whole real number. So this is a string infinitely many long, also infinitely long in both directions. The whole real line. The initial position is x, initial velocity. Then let it go. What happened? At every moment, every point on the real line, what is the displacement that is u? So this is initial value problem. Okay. Okay, let's stop here. I do not have time to solve this problem. Maybe I will make a video of waiting for next